Hi everyone, in this section I'm going to go over the sections 1.4, 1.5 of the Zybook. The fourth section in chapter 1 is about logical equivalence. Let's first define two terms, tautology and contradiction. A compound proposition is a tautology if the proposition is always true, regardless of the truth value of the individual propositions that occurs in it. So, if a compound proposition is always true no matter what the truth value of the single propositions are, that proposition is called the tautology. A contradiction is a compound proposition that is always false regardless of the truth value of the individual propositions that occur in it. So obviously, tautology would be a contradiction, and the negation of a contradiction would be a tautology. So let's look at an example of tautology and contradiction and how their truth tables look like. This is an example of tautology, P or not P. As you see, no matter what the value of P is, the value of P or not P is always true. In the first row, when P is true, not P is false, and obviously the disjunction of a true and a false is true. In the second row, when P is false and not P is true, again, the disjunction of P and not P would still be true. So in both rows, the value of P and not P is true. When all rows have true value for a compound proposition, that proposition is by definition a tautology. In table 1.4.2, you see an example of contradiction. We have conjunction P and not P. We have two cases again. P is either true or false. In the first case, when P is true, not P is false, and the conjunction of a true and a false is a false. In the second row, when P is false, not P is true, and there obviously the conjunction of true and false is false again. So in all rows, the value of the proposition P and not P is false. In all rows, we have false values. Obviously, by definition, that proposition is a contradiction. In this slide, I'm going to formally define the logical equivalence of two compound propositions, and we will see an example using a truth table. So basically, two compound propositions are said to be logically equivalent if they have the same truth value, regardless of the truth values of their individual propositions. For example, let's assume that we're going to show whether these two propositions are logically equivalent. In the left hand side, we have not P or not Q. In the right hand side, we have the negation of conjunction of P and Q. So let's see if we can show whether or not these two propositions are logically equivalent. In order to do that, we need to construct a truth table for both of them. We can, merge the truth table for both of them in one table, as you see here. For both of them, since we have two variables, P and Q, there are four cases that the truth value of P and Q can get. So in each case, we have one row. In the first case, we have the values of P and Q both equal to true. In the second case, P is true, Q is false. In the third case, P is false, Q is true. In the last case, both of them are false. Let's look at the first row. When P and Q are both true, not P and not Q, and the conjunction of P and Q would be true, the negation of conjunction of P and Q would be the negation of true, which is false, and not P or not Q would be the conjunction of, I'm sorry, would be the disjunction of two false statements, two false propositions when we have, and we want to find their disjunction becomes false. So as you see, in the first row, the truth value of both propositions, the left hand side and the right hand side, are equal and both are false. Therefore, in the first row, they have the same truth values. If you continue doing this and look at the second row, third row, and fourth row, you see that in all four rows, they have the same truth value. In the second row, they are both true. In the third row, they are both true. And in the last row, they are both true. In other words, this column and the last column are identical. Therefore, we can say, based on the definition of logical equivalence, the two propositions are logically equivalent, which means that not P or not Q is logically equivalent to not P and Q. This logical equivalence has a name. We call it De Morgan's law. De Morgan's laws are logical equivalences that show how to correctly distribute a negation operation inside a parenthesized expression. Here you can see more laws of propositional logic, which shows a number of logical equivalences that exist between different compound propositions. Each law has a different name. Obviously, you don't need to remember the names, but it's very helpful if you can um, remember the equivalences themselves. For example, uh, the first law is the idempotent law that you see in this table. It has two different forms, the disjunctive form and the conjunctive form. The disjunctive form is this: uh, P or P is logically equivalent to P. You can show this by constructing a truth table for both the left hand side proposition and the right hand side proposition and see that they both have the same truth values no matter what the truth value of P is. We have the same rule, the same law, but in conjunctive form. The conjunction of P and P is again equivalent to P. We have associative laws. The disjunctive form looks like this: P or Q or R is logically equivalent to P or Q or R, which means by changing the place of parentheses, we still have the same truth value. And this is also true for conjunction. The conjunction of three propositions uh, is not dependent on the order of the propositions. You can have conjunction of P and Q first and then R, or you can first get the conjunction of Q and R and then the result can be ANDed with P. In both cases, we have the same truth values. You can see commutative laws. You can see distributive laws. Each one of them can be proved by constructing truth tables. Identity laws, which means the disjunction of P and false is always P. The conjunction of P and true is always P. Same for domination law. Uh, the conjunction of P and false is false, while the disjunction of P and true is true. We have double negation law, which only has one single form, the negation of P. is logically equivalent to P itself. We have complement laws. As you see, the negation of true is equivalent to false. The negation of false is equivalent to true. The conjunction of P and its negation is false. The disjunction of P and its negation is true. We have De Morgan's law, which we saw one of the forms in the previous slide. In this slide you see both forms, both the negation of conjunction and negation of disjunction. We have absorption laws. We have conditional identities. In the conditional identities, we see that the bidirectional statement is equivalent to conjunction of a conditional statement and its converse. Also, we see that a conditional statement can be written as a disjunction of conclusion and negation of hypothesis. So, as again, as I said, you don't need to remember the names. All you need to do is to sort of look at the uh, look at each equivalence and see whether you can prove it or not, and then try to remember it uh, so that later you can use it without proving it. Finally, in section 1.6, I'm going to present some terminology. We first define predicate, a logical statement whose truth value is a function of one or more variables is called a predicate. So it is similar to a logical statement or a proposition, but its truth value is dependent on one or more variables. Okay, so this is how it's different from a proposition. We'll see many examples later. Then the domain of a variable is defined in the following way. We say in a predicate we have one or more variables. For each of those variables we have a domain. The domain of a variable in a predicate is the set of all possible values for that variable that we can replace that variable by those values. So, for example, you can have a variable that has the domain equal to the set of all real numbers, or you can have a variable that can be replaced by uh, a set of all integers. By a variable can be replaced by any integer. Therefore, its domain is equal to the set of all integers. We can have a variable that can be replaced by any, for example, uh, negative integer. Therefore, the domain of that variable would be the set of all negative integers. This is how we define domain for each variable that participate in a predicate. Then we define a universal quantifier. We use a symbol which is the same as upside down capital letter A for representing a universal quantifier. So this symbol is a universal quantifier, and this statement for every x, p of x, is called a universally quantified statement. So basically, we put the symbol of universal quantifier before a variable that participates in a predicate, and then after that, we put the predicate itself. This is how we represent the predicate. P of x represents a predicate in which there is a variable called x. So the truth value of p of x, which is a logical statement, is a function of x, and x is a variable, right? Next, we define a counterexample for a universally quantified statement. A counterexample for such a statement is an element in the domain for which the predicate is false. So, for example, if you have predicate P of X and X has a domain, has a specific domain, if you find a value in that domain which makes the predicate P of X false, that value is called the counterexample for the universally quantified statement for every X P of X. Again, we'll see many examples of counterexamples later. An existential quantifier is represented by the symbol that looks like backward E, this symbol. And the statement that starts with this symbol, which we call it there exists. There exists an X such that P of X is called an existentially quantified statement. So first we use the symbol that looks like backward E, and then X, which is a variable participating in a predicate like P of X. And then we write P of X, which represents the predicate containing only one variable. The predicate P of X has a truth value, which is a function of variable X.